Dr. Anastasia Fialkov, and she's very well known to this community. But I would like to say a few words about her. So Anastasia is currently a senior research fellow at the Kavli Institute of Cosmology, University of Cambridge, UK. She did her PhD at the Department of Particle Physics, Tel Aviv University, and worked with Professor Renan Barkana. And then she moved to Italy at ENS and there she was holding the position of junior research chair at the International Center for Fundamental Physics. And then she moved to Harvard as an ITC fellow at the Institute for Theory and Computation. She has diverse research interests, but mainly focuses on intensity mapping of molecular and atomic lines, with a special focus on 21 centimeter line. And she also works on epoch of reionization and cosmic dawn using 21 centimeter line. But apart from that, she has interest in structure formation, gravitational lensing, cosmic microwave background radiation, and high redshift sources, UV sources, X-ray sources, and their impact on the environment. And today she is going to talk about her research work, and the title of her talk is Unveiling Cosmic. So I now request Anastasia to start your talk.
Thank you, Canon, and thank you for the invitation. I'm actually assistant professor at Cambridge and not research fellow anymore.
Oh, sorry.
So I should update my profile probably.
I took information from your website, so
yeah, I need to update that. Sorry about that. So yes, thank you very much for this invitation, and I'm happy to share my research with this community. And as Canon mentioned, I will be talking about the unveiling cosmic dawn and how can. Sorry. Someone is on mute. If you could mute, otherwise. So I'll be talking about 21 centimeter line and how we model it. What are the updates of our modeling? How do we try to do our best with modeling the cosmic dawn and assessing the impact of first sources on the 21 centimeter line, and then with future or even existing telescopes, how can we probe and constrain this epoch? So because this is quite a diverse audience and I don't know many people, I'll give a brief introduction to the field so that we're all on the same page. And so if there are any students who don't specialize in high redshift universe, I hope they will be on the same page with us after this introduction. So we know that the universe started presumably in a Big Bang, and then there was a period of exponentially fast expansion of the universe called inflation, which led to the universe to be almost homogeneously uniform with only tiny fluctuations in matter density and all the relevant fields such as radiation and distribution of matter that we can see in the cosmic microwave background today. And after cosmic microwave background was released, the universe was nearly uniform, still keep expanding and cooling down with the expansion just because of the adiabatic properties of the gas, say in an expanding volume. So the gas in the universe was at that time nearly neutral, cold, and nearly uniform. Of course, there were small perturbations that grew and developed into the structure finally that we observe today. So the epoch between the CMB decoupling and the formation of the very first stars and galaxies is referred to dark ages, and then we enter into cosmic dawn when the first stars start forming. In the observable volume of the universe, it's roughly about redshift 60 when the very first stars started to form, but the population builds up at around redshift 30 to 20. And then the stars start having impact on the gas around them by reheating and reionizing the universe. So slowly the background gas, the intergalactic medium, transitions from cold and neutral to warm and ionized. And then the stars and galaxies, as they build up and become brighter and brighter, they can ionize the gas as well. And then we transition into the epoch of ionization, when all the neutral intergalactic gas becomes ionized eventually today. So our models today, numerical simulations, describe quite well how the structure forms. Excuse me, could you please mute yourself? Yes, thank you. So they describe well how structure forms transitioning from the cosmic microwave background perturbations to the observable universe today. But we are still quite uninformed about the formation of the first stars. We don't know what processes were exactly in play, because it's very hard to model star formation self-consistently and in numerical simulations. They're costly, and we always need to do some assumptions. For example, properties of stars, such as mass distribution of the first stars, called initial mass function, is not very well understood. So existing observations today are doing quite well. So we have, of course, large-scale structure surveys around us with DES and SDSS and DAISY and CHIME and other surveys probing the universe out to redshift 3 with big cosmological surveys, and we have really exquisite information about the structure and formation of galaxies at those redshifts between today and redshift 3. However, once we push to higher redshifts, galaxies become dimmer and dimmer, and it's harder to observe them. So when we are trying to observe galaxies at ionization, we are actually only sensitive to the brightest ones or lensed galaxies, and there are only a handful of galaxies observed at very high redshifts deep into the epoch of ionization. So today, with HST and also already JWST has some first results, we see galaxies at the kind of deep into the epoch of ionization all the way to redshift 13. That's the highest redshift observable today. And these galaxies should have started forming stars very early on, around 200 million years after the Big Bang. So that would be the stars that start forming at cosmic dawn and forming bigger galaxies that can ionize the gas that we see at redshift 13. So we indirectly have already information about the cosmic dawn through JWST and HST and ALMA observations, and also existence of very bright quasars at redshift 7 to 8 point to the or suggest beginning of star formation at cosmic dawn at redshifts 20 to 30. So this is all indirect. And of course, JWST will push, observations of galaxies are of course direct, but if we interpolate them to calculate when the star formation started, these are kind of indirect indications, and they're also very model dependent. And of course, the hope is that JWST will push this frontier even further, and it might be able to directly observe galaxies out to redshift 20. So probing this cosmic dawn star formation. Other than these observations, 21 centimeter line provides one of the most promising ways to actually not just see these first galaxies, but also understand their feedback on the intergalactic medium, because as I said earlier, stars would heat and ionize the gas. And so we can understand this process of heating and ionization and the impact of stars on the bigger environment around them by mapping the neutral hydrogen distribution and thermal state, so probing the gas between star forming regions. Here on this picture, we see this gray bubbles of ionized gas, and we know that all the space between this ionized bubbles was filled by nearly neutral gas, which was mostly hydrogen, because that's a Big Bang nucleosynthesis composition. We know that the universe is mostly composed of hydrogen atoms. So 21 centimeter line is a transition of hydrogen that is forbidden, and it quickly redshifts outside of the interaction range. So the width of this line is very narrow. If a photon is produced at that frequency, it would very quickly redshift outside of the line width. And so these photons are not absorbed on their way when they are produced, when the signal is created to us. And therefore, we can observe them today with radio telescopes. So this is a 21 centimeter intrinsic frequency, and for gas between recombination and ionization, these photons would redshift to frequencies below 200 megahertz or 250 megahertz, and therefore we need radio telescopes, low frequency radio telescopes, to probe epochs of dark ages, cosmic dawn, and ionization. And so this field is relatively young compared to, say, observations in UV and optical, but it's really entering an exciting stage of when observations actually provide interesting measurements that can either constrain the signal, or we have this first detection that I'm sure you all are aware of from edges, which is still unexplained. But the edges team was sure enough in it to report it in the Nature paper. So it's a very interesting epoch in this field with exciting discoveries. So 21 centimeter, again, is a signal of hydrogen atoms. So hydrogens can absorb or emit into the radio background radiation that is usually the CMB. So this is a radiative transfer problem. CMB photons go through a hydrogen cloud. And if hydrogen is hotter or colder than the background radiation, it will imprint its signature into the background radiation spectrum. So what we actually are trying to observe are spectral distortions in this low frequency radio tail of the background radiation. And by analyzing how the spectral distortions look like, whether it's absorption compared to the CMB spectrum, which is thought to be the best black body spectrum in nature, or if it's emission compared to that spectrum, we can say whether the gas was hotter or colder than the CMB, and also what were the properties of sources at that time. So of course, sources are also non-uniform. At some point, there was only one first star formed in the bulk of the whole universe. And gradually, there are more and more sources produced, but they're first produced in the overdense regions, which are rare. So first star formation is patchy, and therefore also the backgrounds that are produced are very non-uniform. And this non-uniformity varies with time because sources build up and the photons they produce change. So radiative backgrounds evolve as the universe evolves. And this non-uniformity is also imprinted in the 21 centimeter signal. So we can study how fluctuations in these backgrounds are seen in the 21 centimeter signal, and then interpret what actually tells us about the universe itself and the star formation and galaxy formation. So when we calculate 21 centimeter signal, or if you want to interpret the observation, we need to be aware of the main processes that affect the signal. And if you solve this radiative transfer equation, you'll get the simple or relatively simple equation that is on the bottom right of the slide. This gives us differential brightness temperature, so the 21 centimeter brightness minus the background radiation. And to the leading order, it's proportional to the neutral fraction, so amount of neutral gas in the universe, because it's produced by neutral atoms. This function is very close to 1 all the way through dark ages, cosmic dawn, but then it drops quickly as the universe reionizes by massive galaxies that HST and JWST already see. And then there are several terms that come out of this radiative transfer equation again. There is a radio background temperature that just, if there are no sources that affect it, if that's just CMB, it would redshift with as the universe expands, so photons lose energy, and the background temperature just decreases monotonically with time. Okay, and what sets the 21 centimeter contrast with the background radiation is how hot the gas is. So it's gas temperature that is first coupled to the temperature of radiative background, but then by residual electron fraction. So there is some small percentage of atoms that are still ionized, and they would interact with radiative fields with CMB, and this would be enough to couple the gas temperature to the temperature of the radiation at cosmic dawn and shortly after recombination. But when these reactions become rare, gas would cool faster than the radiation just from thermodynamics. And so at this time, 21 centimeter would be seen in absorption. However, once we have a population of sources that can heat up the gas, this gas temperature would turn over and be above the the radio background temperature. So overall, we would get emission signal. However, this coupling to the gas temperature of the 21 centimeter signal is only possible when there are enough Lyman alpha photons created by stars, because they enable this coupling between gas temperature and the characteristic temperature of the 21 centimeter signal. And so we do need stars to see this deep absorption profile. And the existence of this deep absorption profile is a signature of the first stars. We wouldn't have one without the other. Without stars, 21 centimeter signal would be just coupled to the gas to the temperature of the radiative background, and we would see nothing. So of course, I mentioned that it's also non-uniform, and every one of these backgrounds in this equation also fluctuate in space and in time. And the character of these fluctuations depends on the properties of each type of radiation and each type of sources. For example, Lyman alpha photons can only propagate out to around 60 megaparsecs around the sources. So they would couple the spin temperature to the gas temperature only within this volume. And we need a lot of sources to produce Lyman alpha to have coupling around the whole sky. While heating, X-ray photons can propagate even to thousands Komovin megaparsecs and heat up the gas on much larger scales than Lyman alpha coupling. And we also know that UV radiation has very short mean-free path, so UV photons would first start ionizing the gas very close to the sources, imprinting tiny ionized bubbles, and then only slowly growing as more massive galaxies appear. So that's why it takes much slower for reionization to affect the 21 centimeter signal compared to Lyman alpha and X-rays, which start affecting it very early in cosmic dawn already. And of course, if there are radioluminous galaxies, if there are any radio sources such as AGN or other that produce radio photons, these radio photons would be added to the background radiation and change the shape of the 21 centimeter signal. So for example, if in this slide, the green line has some contribution from sources and starts growing, if radio galaxies produce radio photons proportionally to star formation rate, the shape of the 21 centimeter signal, that is the green background minus yellow line, would be completely different. So we need to take all this into account when we model the 21 centimeter signal. There are several types of statistics that one can study about the signal. Of course, as with the CMB, people look at monopole, which is the black body, and they also study fluctuations, and they also look at the higher order statistics. With 21 centimeter signal, we can do the same, but at every redshift separately, effectively. So one of the easiest or simplest statistical properties is to study the global or spatially average signal as a function of redshift. And this is called the global signal. And that's what the EDGES collaboration reported in 2018. So it's still unverified, but that's the only available detection as of now. And so the signal, as I already mentioned, has some characteristic features. For example, it has, in all simulations that we run, it has this deep absorption profile typically, that is a signature of Lyman alpha coupling and X-ray sources. And then there is usually a heating signature when signals goes into emission. And then sources ionize the gas, so the signal gradually disappears. So this shape is generic, but the depth and the location of each one of the peaks and troughs here changes with the properties of star formation that we assume, and also what type of radio background we assume in the simulations. We can also study fluctuations. For example, if you fix co-moving angular scale and study how the fluctuation on this scale evolve with time, you would see that again, because of the non-homogeneity of sources and different effective horizons of each type of sources, we will have structure of peaks and troughs in the power spectrum at fixed co-moving angular scale. And then these peaks, each one can tell us about the properties of Lyman alpha sources and how they were distributed, X-ray sources, and what was the even spectral energy distribution of the sources, and then ionizing sources. And of course, if you add radio background sources, they will also affect the structure of this spectrum. There is a lot of observational activity. I adopted the slide from Leon's recent paper. Of course, remote telescopes in India, also GMRT and others that try to measure the both global signal and power spectrum. Yeah, we'll be talking about this more, of course, but you all know about Sarah's group in Bangalore that recently refuted the EDGES signal at 2 sigma. So they measured the signal in the same frequency band, roughly overlapping with the EDGES band, not completely, but partially. And they don't see the signature. So that's a very interesting development in the field. And the fact that they don't see the signal allows us to rule out some of the most exotic models that we have right now and putting constraints on astrophysical parameters for the first time. There is also an effort in Cambridge, which I'm part of, to put an antenna in the Karoo Desert in South Africa, even 2 different antennas of different configurations and design. And there is already 1 antenna placed there taking data. So this is a new development in the field. And of course, there are several power spectra experiments that are also have already published upper limits, such as HERA, LOFAR, MWA, and there is NANUFAR in France, which is a LOFAR station, but with more antennas in the core, so it's more sensitive, and it actually measures the signal at the cosmic dawn frequencies. It's a more challenging experiment compared to HERA, MWA, and LOFAR, which at the moment measuring at the epoch of ionization, because the foregrounds are stronger and the signal is as strong as during the EoR. So overall signal to noise is lower at cosmic dawn for some signals. But at the moment, NANUFAR and LIDA also are the only experiments trying to observe cosmic dawn signals. So as I said, the EDGES signal has been refuted, but if it was true, or if we measure something else at the same frequencies corresponding to redshift 17, that would be an indication of star formation at cosmic dawn at around redshift 20. And of course, that would be fantastic news and really exciting. So from the structure of such a trough, we would be able to measure when star formation started, by looking at the onset of this shape. So through Lyman alpha coupling that couples 21 centimeter signal to the cold gas, we would see the onset of this global absorption. And then when it climbs out of the absorption, that would be the X-ray heating epoch. So we would be able to constrain star formation and also X-ray heating. However, at the moment, so just for completeness, I need to mention that the edges signal is much deeper than anything what we predict for models where the cosmic microwave background is the radiative background. And so to explain the edges signal, one would need to add terms or to add contributions either to gas temperature to lower. So because 21 centimeter is a contrast between background radiation and gas temperature, at the end of the day, we need to either raise radio background or lower gas temperature. Both would be able to explain the edges signal. So there were several papers, many papers coming up with explanations in terms of dark matter interactions, for example, which can cool the gas, lowering the gas temperature. Also sources such as either astrophysical, bright quasars or radio galaxies, or exotic such as sterile neutrino or dark matter annihilation that would add up radio backgrounds. All these explanations to my taste are extreme, but they are valid theories that can be probed with 21 centimeter cosmology already today. For example, with SARAS non-detection, we can put limits on all these exotic theories. So there are, because edges detection was such a big thing and really exciting and mysterious signal, there are many telescopes that are trying to probe and verify the signal again. So I already mentioned SARAS data that doesn't, that refutes the signal. There are several power spectra experiments that can actually hope to probe the universe at the cosmic dawn redshifts and thus probe the signal in absorption in the power spectrum. And also REACH in Cambridge maybe will help to see if there is any signal at cosmic dawn. So I'm sure Surab gave a talk in this group about SARAS. This is just to show you their data. And so they don't see edges signal. But if edges, if there is anything in those redshifts, then we would also search for compatible power spectra signals. So for example, we predict both global signals in our models in exotic scenarios that are compatible with edges and corresponding power spectra, and such power spectra would be in the sensitivity band of the SKA or maybe non-EoR, and therefore we can indirectly probe the cosmic dawn signals through power spectra as well. So far, there are several upper limits at the epoch of ionization, as I mentioned, from power spectra experiments, and the strongest one at the moment is HERA. So we did some work in comparing these exotic models with boosted signals, for example, with extra radio background, and seeing what HERA can say about these models and how can we constrain the scenarios with the HERA data. However, even HERA, so HERA is at redshift 8 to 10, and it does have pretty strong constraints on these radio background models that have boosted signals. But these models that are constrained by HERA actually cannot say anything about edges because it's just a different redshift range. And the signals that would be strong in the edges band, they actually decay by the time HERA measures the signal, so they would not be visible in the HERA band. So this is a summary status for the cosmic dawn observations. So there is some from LOFAR and other experiments. So how do we, if we measure the signal or if we have strong upper limits, what can we say about actually astrophysics? So I already hinted that 21 centimeters rich signal that depends on gas temperature, Lyman alpha photons production, and ionizing photons. So we can build models that have detailed galaxy population evolution, star formation evolution, and evolution, and see how this detailed models actually, what kind of signals they predict, and how can we test properties of first stars using the 21 centimeter signal. So that's what I've been doing also in the last many years. So the 21 centimeter signal, it is sensitive to the backgrounds, and the backgrounds are actually a compilation of radiation produced by sources since the very beginning of star formation. So it's not instantaneous. You cannot just take radiation at specific moment and calculate the 21 centimeter signal, because also star formation within the whole past history of the universe would contribute to the values of X-ray and Lyman alpha backgrounds at that specific redshift you're interested in. So that's an integrated effect, and we need to take into account the whole evolution of star formation and gas temperature. So therefore, we run numerical simulations that start at some initial redshift before star formation, and then they integrate over star formation and the corresponding emissivities of stars, amount of photons that they produce. We take into account the redshifting of this radiation when we compute radiative backgrounds at each specific redshift, and then infer the 21 centimeter signal. So I show the slide. So that's just to summarize that we need to calculate Lyman alpha background, ionizing background, gas temperature. So there are many components that contribute to gas temperature, and eventually make assumptions or calculate the radio background signal. So if we only have CMB and no stars, we would have no signal, as I mentioned, because the radiative temperatures would go into equilibrium, and the 21 centimeter spin temperature would tend to the temperature of the radiation. So we do need to add stars, and that's what adds this absorption trough. And then the signal is sensitive to the ratio of the radio background to gas temperature. So once we have stars, we expect to see this Lyman alpha coupled bubbles in the 21 centimeter signal, as we can see on the right here, big coupled bubbles of gas seen in the 21 centimeter signal, as opposed to 0 everywhere else where the 21 centimeter couples to the temperature of the radio background instead of the gas temperature. So this type of bubbles can be maybe imaged by the SKA in the future, and they would be a direct probe of star formation at redshifts of cosmic dawn, so about 25 to 20. And this is a very pure probe, because at that time it is unlikely that X-rays or any other sources or UV sources contaminate this Lyman alpha signature. And so that would be a probe of star formation and the efficiency of star formation in the first star forming small dark matter halos. Another effect that we need to be aware of is once Lyman alpha photons are produced, they would also heat up the gas through the effect called Lyman alpha heating. There is actually heating and cooling by Lyman alpha photons, because they are produced and then they can scatter multiple times, even 10 to the 6th number of times typically. And so they carry some energy with them, and they can affect the temperature of the gas. And if you just have this Lyman alpha heating effect without any other heating in the universe, these photons alone can heat up the gas to the temperature of 100 Kelvin compared to the vacuum temperature today that is 2.7 Kelvin. So it's a non-negligible effect, and especially important to take into account when we don't have any other heating sources, such as X-ray sources. So we did that in the recent paper with Itamar Rees, who led this work. And we evaluated how strong the effect of Lyman alpha heating is compared to the simulations when it's not taken into account. And here the black lines are the lines from our previous work that do not take Lyman alpha heating into account. So this is a wide scan of astrophysical parameters, and we ran many simulations to study the ensemble of models. And then the blue lines are the models which do take Lyman alpha heating into account. And so you can see how strong the effect is on the kind of ensemble of models. So specifically, the very deep absorptions are not there anymore. So to have this deep absorption, again, you need to have strong Lyman alpha background created by stars and very cold unheated gas. But this scenario actually is not physical anymore, because once you have strong Lyman alpha background, the gas will be heated up as well. So we don't have this deep absorptions. And we have a minimum of the signal that is defined of the kind of the asymptotic minimum that is defined by this Lyman alpha heating in the absence of any other heating sources. So this Lyman alpha heating effect has it's important, especially for current observational constraints that are made from Hera and from Saros, for example, because both Hera and Saros are sensitive to the strongest signals. And so Hera is measuring at the redshift of 8 here and 10. And so the first signals that it would constrain are the coldest scenarios, which are no more physical because they don't include Lyman alpha heating. So the signals are a bit reduced by this effect, and therefore our observational constraints are affected by it as well. So we can also study more properties of star formation and the populations of stars. For example, what the initial mass function of the first stars was, and how the population transitioned from population 3, which are the very first stars formed from chemically pristine gas, how this population enriches the gas with metals by exploding in supernovae, and then the star formation becomes different. So there are people think that population 3 stars are very massive because of the star formation in pristine gas properties. But once the gas is enriched by metals or chemicals, the fragmentation of gas is different, and so we form much more smaller stars than bigger stars, and the initial mass function of the population of stars changes with redshift. And this also would affect formation of X-ray binaries and X-ray heating. So we are looking into these details with my students at the moment. And what we did was to explore how initial mass function of the population 3 stars affect the 21 centimeter signal. So today we know that in our galaxy, most stars are below 1 solar mass, so they're mostly small stars. So 89% of stars are in small stars. But as I said just a few moments ago, that might not be relevant for the first population of stars formed. So population 3 stars initial mass function is not very well understood yet in simulations. And on this chart, you can see how the range of masses of population 3 stars generated in simulations evolved with the year of simulation. And so first people thought that they would be very massive, but then as more high resolution simulations were produced, the initial mass function actually evolved with the simulations. And so today we think they're more like between a few tenths and subsolar masses. And of course there is distribution, so it's a distribution of masses. So in our work, we took several typical examples. So at present day, IMF, close to present day, and then top heavy, so a very flat IMF that mostly composes of very massive stars, and then 2 intermediate examples. And we explored with my student Thomas Geshe-Jones how these IMFs would affect the emissivity of first stars. So this is an example of the spectrum that star produces as a function of stellar mass. And you see that for different stellar masses, the spectrum changes. And so especially for small masses, there is a stronger change, while for very big masses, the spectrum is roughly mass independent. And then Thomas looked at different initial mass functions, so integrating the spectra over the shape of the distribution of stellar masses. And so these are several examples that we are getting. So then we looked into how this stellar masses would affect the 21 centimeter signal and power spectrum. And because again here, because of this panel here, you see that there is again no sensitivity to high masses, but sensitivity in the spectrum to lower masses. We also see that in the 21 centimeter power spectrum, when we assume a fixed stellar mass, the spectrum for the assumed very low stellar masses, this dark blue one, for example, is very different from the very heavy masses, the yellow ones. But there is very little change for stars of heavy masses. So between, say, 60 to 500, most spectra look the same, while then there is a very big gradient for smaller masses. So if the initial mass function is bottom heavy with many small stars, we might see the signature of the IMF in the 21 centimeter signal, while it is, if it's dominated by very massive stars, we won't. So you can see the details in the paper. Another thing we looked at is the transition between population 3 and 2 stars. And so that would depend on the properties of the first supernovae, how energetic they are, and how quickly the gas, so supernovae can expel gas from halos, because the first stuff, I mean, halos are very small, and then the gas would recollapse. And so after it recollapses, population 2 stars are started to form. And so how quickly this gas recollapse actually affects the shape of 21 centimeter signal. And so on the right here, you can see the variety of models of the global signal with different assumptions for the stellar, for the gas recollapse. So we see that the 21 centimeter signal can be sensitive to this parameter of early star formation as well. So I'm running out of time, I guess. I don't know how much time do I have.
Anastasia, you still have 10 minutes if you
okay, great. Yeah, I will take them. This part. So then another thing we looked at was a population of radio galaxies. So they don't have to be so extreme as to explain edges, but even if we have a weak radio population, they would alter the background signal, and so they would make changes to how the 21 centimeter signal looks like. So we again with Itamar Rees looked at this in 2020, and we modeled the population of radio galaxies with the radio background increasing with star formation rate. So as more stars are formed, the stronger the background becomes. And so because now you have radio source within every galaxy in this model, also the structure of line alpha coupled bubbles actually changes. And so you can see the difference between a uniform radio on the left and the radio background when there are radio galaxies in every halo on the right. And so we see much deeper radio bubbles which have a radial profile. So it's not uniform background, but the strength of a 21 centimeter signal depends on the radial distance from the halo center in every bright spot. So we'll look at different scenarios, and even for relatively mild backgrounds, such as this orange line, we get some interesting signals, and the signal depends on whether the sources are non-uniform or if the radio background is uniform. So dashed lines here are the uniform background, and solid is the non-uniform background. This bottom black line is the CMB only case, and all the colored lines have different assumptions for radio strength of this radio background model. And only the most the strongest backgrounds can explain edges, while this orange line is too weak to explain edges, but it's strong enough backgrounds to modify the shape of the 21 centimeter signal. So I already showed this plot. So here we took very strong radio backgrounds, and then we can, with this model, explain edges signals and produce corresponding power spectra that could be probed with low FAR or nano-FAR, HERA, or the SKA. So this set of models for very strong radio backgrounds are of course very exotic, but they are also interesting because we can already probe this model with existing upper limits from HERA and SARAS, and we can start using this. We can use these models to develop our pipeline and see how data behaves with the model. How can we put constraints? What kind of numerical tools we need to use, Monte Carlo or other methods, Bayesian analysis, and how do we constrain parameters of the universe using the existing upper limits, even though this model might be a bit extreme on the strong radio background side, but it's still very interesting test case to explore. So we looked at it with HERA data, and here you see a collection of power spectra, color-coded with respect to the likelihood in terms of HERA data. The data points here are the HERA measurements. And this black line here is the amplitude of models without the radio background added. So it's the CMB only case. And you see that in our models with the Lyman alpha heating, CMB backgrounds models don't exceed HERA data points. So they would not be able we would not be able to constrain this model with HERA. But if we add radio background, then there are many models that do exceed the HERA data, so we can put limits and constrain parameters. So purple here are models that are consistent with HERA, and orange are the ones that can be ruled out. And we also use a lot of neural networks to go from the ensemble of models to a smooth dependence of the signal on the astrophysical parameters, which then allow us to use the simulators in MCMC and Bayesian analysis and put constraints on the model parameters directly. So we did that with HERA data, and we can see that there are, you can see here on the bottom a triangle plot for our model parameters. So 2D distributions, two-dimensional parameter posteriors when we integrate out the rest of the parameters. And these lines on top of each column correspond to the one-dimensional probabilities for every parameter specifically. And we look at star formation efficiency, minimum mass or velocity of star-forming halos, X-ray heating efficiency, CMB optical depth, and this strength of radio background produced by every galaxy. So by looking at the 1D PDFs, we see that some of them are flat. So for example, for minimum mass of star-forming halos, HERA cannot say anything. Also tau and F star are pretty flat. But there are two parameters, that is X-ray background strength and radio background strength, that are clearly constrained by HERA. So HERA rules out models with very strong, very weak X-ray radio background and very strong radio background, because these are the models that produce the deepest absorption or the highest power spectrum. So they are these orange models that are the easiest ones to rule out. And so that's very interesting. And we can also look at in terms of the temperatures. So comparing gas temperature and radio background temperature, we can look at our priors. So prior is not flat here because our priors on the astrophysical parameters are flat, but when we talk about temperatures, they're completely non-flat. But we can compare with the posteriors, the blue ones, and we can see that this orange region was not was ruled out by HERA. So these models that have relatively cold gas and relatively strong radio background are inconsistent already with HERA. So we also can say that HERA is complementary to other surveys. For example, Chandra X-ray survey provides information about radio X-ray background. So there is a portion of X-ray background measured by Chandra that is unattributed to any sources. So there are no source population that can say they can say the X-rays are coming from. And so this can be interpreted as a contribution of very high unresolved X-ray sources from high redshifts. So this would put an upper limit on how strong the X-ray population and high redshifts can be. And so here we can see that this crosses models that are crossed, they're ruled out by this Chandra X-ray background. Such models would over-predict this X-ray background and be observed by Chandra. So they are ruled out by Chandra, but they are consistent with HERA. So they are colored purple, which means they're in this model range, which are consistent with HERA observations. On the other hand, there are models that are consistent with Chandra, but inconsistent with HERA. So these orange dots are okay for Chandra X-ray background, but they're ruled out already by HERA. And there are also models that would exceed the radio background, such as observed by Arcade. So they're also inconsistent, and they are empty dots here. So there is kind of interesting synergy between these different telescopes, X-rays, radio background, and the 21 centimeter signals that break the plane of these astrophysical parameters in terms of sources that hit and produce radio background radiation. So we also looked at signals, at global signals, and we have, of course, data. Saurabh has data from SARAS-2 and SARAS-3, and this data can be used to put constraints on the astrophysical parameters as well. So here we have SARAS-2 constraints, and we can see that SARAS-2, the blue contours here are again the prior ensemble of signals, and the red are the ones that are consistent with SARAS-2. And we see that SARAS-2 can already rule out all this big part of the astrophysics of the space of the signals that we modeled. They're extreme, but they can be already ruled out by the SARAS data. And this data puts some constraints on the astrophysical parameters already, so they're still weak. So the 1D PDFs are pretty flat, but we can see in the 2D PDFs that there is some regions that are ruled out or compatible. So there is discrimination between astrophysical parameters by SARAS as well. We have already results with SARAS-3 also, but it's still not published, so I will not talk about that much. They are complementary to SARAS-2 because SARAS-3 is at a higher redshift range, and so it constrains different signals and probes different type of astrophysical parameters. But stay tuned, it hopefully will come out soon. And I'll stop here with my conclusions. So I showed you hopefully that 21 centimeter is a very promising signal, sensitive to various astrophysical sources and properties, and can be an interesting probe of the first population stars, first supernovae, first radial sources. And there are already some very interesting constraints coming from current generation of experiments, such as HERA and the SARAS-2 and 3 experiments. And thank you very much for attention.
Thank you. It's a very nice talk.
Thank you.
Okay, now it's time for questions. So if you have any questions, please press the raise hand button. Any questions, comments? Okay, so Borun Maiti has a question. Borun, please ask your question. You just unmute yourself and then ask your question.
Am I audible?
Yes.
So I had a question about the slide where you show the effect of Lyman alpha heating. So it seems that Lyman alpha heating is mostly affecting the reionization rather than the cosmic dawn portion. So presumably I would think that it should be opposite, right? That Lyman alpha should affect the cosmic dawn mostly, and the reionization should not be affected that much.
That's a very good question. The reason is that so Lyman alpha coupling happens very fast, right? But Lyman alpha heating, you do need to accumulate a very strong Lyman alpha background to matter, actually, because the effect on heating is much weaker than on Lyman alpha coupling. And so the effect starts at high redshifts, but it's weak, and it only builds up to lower redshifts. So actually the effect on gas temperature becomes important only at lower redshifts, actually, interestingly.
Okay.
So thank you, very good question.
Any other questions?
Kushum is not here, but he sent one question in the message. When you change the initial mass function of the star formation, it is expected that the stellar evolution and the next set of star formation physics, including the metallicity, etc., will also change. Is this also taken into consideration?
So we're building up this model at the moment. We have the dependence of the Lyman alpha background on the initial mass function, but we are still working on the X-ray population. And because there is so much uncertainty in the population 3 stars, we kept population 2 fixed, so we didn't vary those properties yet. But I completely agree with you that it should be modeled eventually self-consistently.
Okay, thank you.
Thank you.
Any other questions? Actually, I have one question. So at some point you said that this Lyman alpha coupled regions are the size of those regions are of the order of 60 megaparsec, you said, right?
Roughly, yes.
Yeah. So why the Lyman alpha photon propagates stops at this 60 megaparsec, not propagating further?
Because they redshift, right? So if they are only the photons produced within some frequency range will contribute to Lyman alpha coupling, because either they are, so if they are initially redder than Lyman alpha, they will not contribute, or only if the velocity is right, they will be seen by the gas as Lyman alpha. So there is a wing that does contribute, but it's narrow. And the photons that are bluer than Lyman alpha, they will, if they go into, if they correspond to any other hydrogen lines, they will be absorbed by the line and cascaded into Lyman alpha, or they will just redshift into the Lyman alpha. So there is a narrow redshift range of photons that is translated into about 60 megaparsec. It's redshift dependent number, but they cannot infinitely propagate because they either redshift or they enter into a different Lyman alpha line and then cascade.
I see. But when it enters into different Lyman alpha series and then cascades, it will eventually, some of them will eventually convert into Lyman alpha, right?
Yes, but it's still very narrow frequent redshift range, and it's a like small tail.
Oh, I see.
So if you calculate PDF of these photons versus the horizon, we have this in the paper. So number of photons that reach different radial distances from the source, we have this in the paper if you are interested. There is a tail, but it drops pretty quickly. So 60 is roughly the typical number that I quoted, but there is a tail that extends a bit further, of course.
Okay, so that means at very early, very high redshift, even if you have enough number of Lyman alpha photons, it will not help to couple the CMB temperature, couple the spin temperature with the gas temperature, because of
Right,
this.
exactly.
Yeah.
So as you can see here, there are regions that are
Yes.
zero, right, because of that.
Mhm.
So because you cannot infinitely propagate Lyman alpha photons.
So we have to wait for other sources to form in between.
Right.
Okay. Thank you.
Thank you.
And then there is a question from Rajesh. Rajesh, please unmute yourself and ask question.
Hi, Anastasia. So
Hello.
from this figure, it seems that the bubbles, the heated regions are exponentially decaying. Is it right or is it uniform?
So here there is no heating at all in this picture. Here we only took into account Lyman alpha physics.
Okay. And you when you are talking about this Lyman alpha coupled regions, will there how is these regions? Is it completely coupled or is there any internal structure that I'm?
So there is of course probability to couple, right?
Yes.
It's not assumed that they are completely coupled. There is a scattering probability. Monte Carlo code that calculates whether photons scatter multiple times, and Itamar calculated what will be the scattering probability to a different angle and distance, and it's a statistic in a statistical sense. So there is no assumption of fully coupled.
Okay. Okay, and another thing about this, how do you model the excess inhomogeneous excess radio background model?
So that is modeled. Also, there is a model for radioluminosity per star formation rate. So in every galaxy, we know what star formation rate is, and then you can scale the radioluminosity accordingly.
Okay.
Right, and so attributed to every source.
Okay. Okay. So you uniformly distribute around the sources, the radio background.
No, it's not uniformly. There is a
Okay.
radial dependence.
All right. Thank you.
Mm-hmm.
Any other question? If not, then let us thank Anastasia for her very nice talk. So thank you. Thank you, Anastasia.
Thank you.
So
Thank you very much for
yeah.
having me.
Yeah. So we'll stop